Hello dear students, good morning. Welcome back to the chemistry class. In the last class we have discussed about the concept of vapor pressure, its definition, factors affecting and Raoult's law for two different solutions. Solutions containing volatile solute and the solution containing non-volatile solute in detail. So in this session we are going to deal the next concept, that is ideal and non-ideal solution, a few points of difference, and a small concept, azeotropic mixtures, a very small concept. Now let's take the next heading, that is ideal and non-ideal solution. Ideal and non-ideal solution. Ideal and non-ideal solution. So here in this concept we need to define what is meant by the ideal solution and non-ideal solution and few points of characteristics. So definition and characteristics of these solutions we need to discuss. So let us deal first point. Ideal solution means what? So let us make two columns: ideal solutions, and non-ideal solutions. Non-ideal solutions. First one, ideal solution and non-ideal solution. Ideal solution and non-ideal solutions. So here, what is meant by the ideal solution and what is meant by the non-ideal solution? The first point is a definition. First point, definition. Let us define the ideal solution. Very simple definition. The solution which obeys the Raoult's law over the entire range of concentration is called as ideal solution. The solution must and should obey a Raoult's law over the entire range of concentration is called as ideal solution. Solution means, what is the definition? The solutions which obeys a Raoult's law, over the entire range of concentration, whatever the concentration, irrespective of the concentration of solution. Solution means it is mixture of two or more components. It must and should obey the Raoult's law. That means if two components are there, A and B, so PA is equals to P naught A into XA. What is the Raoult's law? Raoult's law statement: partial pressure of any component is equals to P naught of that component into Xi. It must and should obey Raoult's law over the entire range of concentration is called as ideal solution. Then definitely the solution which do not obey Raoult's law over the entire range of concentration. So here the solution which do not obeys Raoult's law, are called as non-ideal solution. Ideal solution and non-ideal solution. See here, so this is the first point of difference between ideal and non-ideal, which obeys Raoult's law, which do not obey Raoult's law. Now some other characteristic properties of this ideal and non-ideal solution, if it is considered. So in this case, ideal solution, the intermolecular interaction between the two pure components before mixing and the interactions after mixing are same. That means, suppose if I am mixing two components, if I am mixing A plus B, this gives us to the solution AB. So here in this case it is a component A. So here there is an interaction between A and A, whereas B interactions, the intermolecular interaction, and in solution there will be interactions between A and B. If ideal solutions are okay, first point, if the intermolecular interactions of A and B components, that is pure components, are similar. Now, the ideal solutions are formed by the mixture of pure components. There is a conditions. So the components which forming the solutions must be identical in shape or similar size, and the intermolecular interaction must be similar. Then only which forms the ideal solutions. If the intermolecular interactions in pure components A and B and AB, if all the interactions are same, that is said to be ideal solution. That means intermolecular interactions, intermolecular forces, attractive forces in the solution. So in this case, the second point, intermolecular interactions, intermolecular interactions. Intermolecular interactions of AB, intermolecular interactions of AB, AA and BB are same. Intermolecular interactions of the solutions is the same as that of the pure components, whereas in this case, so here the intermolecular interactions of AB is not same as that of intermolecular interactions of AA and BB. In simple words, intermolecular interactions are same in this case, whereas in case of non-ideal solution, the intermolecular interactions are not same. So here intermolecular interactions will be different. It may be greater or it may be lesser. So here it is not same as that of pure components. Now according to the Raoult's law, if it is said, so in this case the total vapor pressure exerted by the solutions is always equals to PA plus PB, that is according to the Raoult's law. But in this case the total vapor pressure is not equals to PA plus PB. So it is something different. It may be greater or lesser than as calculated according to the Raoult's law, calculation by the Raoult's law. Now, some other features, that means here enthalpy change of mixing, H mixing or V mixing, enthalpy of mixing of volume is equals to 0, whereas in this case delta H mixing and delta V mixing is not equals to 0. Let us explain these 2 points. So enthalpy of mixing, that means here first A plus B used as to AB. In thermodynamics we have studied that calculation of enthalpy of a reaction. So here enthalpy of a reaction. So in this case bond enthalpy, how much energy is required to break the bond? Bond enthalpy. What is the formula for bond enthalpy? Enthalpy change delta H is equals to sum of enthalpies of reactant minus sum of enthalpies of product, right? So in this case, in the case of ideal solution, intermolecular interactions are same, that means bond enthalpies of reactant and the product, that is solutions, is the same. So if it is same, then a reactant minus product is equals to 0. So let's say its value is x and its value is also x. Therefore, delta H mixing is equals to 0 in case of ideal solution. Similarly, let's say 10 ml of A is mixed with 10 ml of B. This gives 20 ml of solution AB. 20 ml of solution AB volume. So here in reactant side total volume is 20 ml and product size total volume is also 20 ml. Therefore the change is 0. 20 minus 20, that is equals to 0. Enthalpy of mixing is equals to 0. Volume upon mixing the component is also equals to 0. But in case of non-ideal solution, it is not equals to 0. Is it clear? So ideal and non-ideal solution. The first point is definition. What is the definition? The solutions which obeys Raoult's law over the entire range of concentration is called as ideal solution. If the solution which do not obeys the Raoult's law, it is non-ideal solution. Now, in this case, intermolecular interactions of a solution and pure components are similar, whereas in this case, the intermolecular interactions of the solutions will be different from its pure components. Whereas next one is here the total vapor pressure calculated will be same as expected from the Raoult's law, but in this case it is not same. Next is delta H mixing and delta V mixing is equals to 0 in ideal solutions, whereas in case of non-ideal solutions delta H mixing and V mixing is not equals to 0. So these are the some points of difference between ideal and non-ideal solution. Ideal solutions are formed by the mixture of two or more components which are having identical size, identical intermolecular interaction and identical structures. So those can form the ideal solution, whereas non-ideal solutions, if the mixing components or the components with having a different structures, different intermolecular interactions, then it forms non-ideal solutions. Okay, so this is about the concept of ideal and non-ideal solutions. Now we are saying that non-ideal solutions, in case of this non-ideal solutions, here it is of two types. In non-ideal solutions which showing positive and negative deviation, if intermolecular interactions are not same, that means the intermolecular interactions of these solutions, it may be greater than pure component or less than pure component. Total vapor pressure calculated, it may be greater or lesser. Not equals to 0 means it may be greater or it may be lesser. Same, delta H mixing and delta V mixing, it may be greater or lesser. So here non-ideal solution showing positive and negative deviations. Now in this case, the non-ideal solutions, non-ideal solutions, very simple concept here. Non-ideal solution showing positive deviation and non-ideal solution showing negative deviation. Non-ideal solution showing positive deviation and negative deviation. The solutions which do not obey Raoult's law, so both positive and negative, these solutions do not obey the Raoult's law. Intermolecular interactions of AB component is always less than the intermolecular interactions of AA and BB. So positive deviation means what? Negative deviation means what? First we will clarify this concept. So here look at this. The vapor pressures. So in a closed vessels, when a solution is heated, it forms some vapors. And this is vapors. Pressure exerted by the vapors. This is a vapor pressure. Now, if two components I am mixing, A and B, if the intermolecular interactions are very less as compared to pure components, suppose in one case it is component A, in second component it is B, this one is A, B, and when it is mixed, so this is the solutions AB, this is the solutions AB, three components I have taken in all the case. So here it is PA and it is PB. When it is mixed, so it is partial pressure of A plus partial pressure of B. Look at this. if the intermolecular interactions are strong in pure components A and B, intermolecular interactions are very strong, then the molecules do not have a tendency to escape into the vapors. So therefore vapor pressure will be less. So in these two cases, the vapor pressure will be less. So therefore the expected vapor pressure of the solutions will be less. But when these two are mixed, if the intermolecular interaction decreases, so intermolecular interaction decreases, so what happens? Very less energy is required. So these having high tendency to escape because the force of attraction is less. So therefore in this case the vapor pressure will be more than expected one. So the total vapor pressure in solution is greater than PA plus PB. That is called positive deviation. If more than expected, it is positive. If less than expected, that is called negative. See, if two liquids, if in the intermolecular interactions in solutions, if it is more than pure components, intermolecular interactions are very strong. So what happens? If intermolecular interactions are strong, then these molecules which do not have high tendency to escape. So therefore vapor pressure will be less than expected one. Hence it is called negative deviation. So now in this case, so positive means the intermolecular interaction between the A and B component is less than pure components, then only the solutions molecules which are readily undergoing vaporizations. So vapors are formed readily. These having high tendency to escape from the liquid surface. Therefore vapor pressure will be more than calculated value. Calculated values is more than according to the Raoult's law. P, total pressure, in this case intermolecular interaction is less, so therefore the total pressure will be greater than PA plus PB. It is greater than PA plus PB, therefore it is said to be a positive deviation. Positive deviation. Whereas in this case negative deviation, the intermolecular interactions will be greater than the pure components AA and BB. So when the intermolecular interactions are stronger than pure component, vapor pressure will be reduced. So total vapor pressure is less than PA plus PB. PA plus PB. So this is the positive and negative deviation. Some other features. So in this case, delta H mixing and delta V mixing. Delta H mixing, in positive case it is greater than 0, whereas in negative case it is less than 0. Delta H mixing and V mixing, volume and enthalpy, is less than 0, less than 0. See that positive deviation, intermolecular interactions are less, the remaining is greater, greater, greater. In positive, greater than ideal. In negative, less than ideal. Negative, in case of negative deviation, smaller than or less than, less than, less than. Only intermolecular interaction will be strong. Now let us have let's go for this explanation of these two concepts. H mixing, enthalpy of mixing is greater than 0. So enthalpy of mixing, see the amount of energy required to break the bonds in AA plus BB, this gives us to AB. Intermolecular interactions are less than AB, that means so this bond enthalpy will be lesser as compared to A and BB. So therefore enthalpies of reactant and products, if it is considered, so some amount of energy will be required. It is positive or negative, so it is greater than 0, because suppose let's say the bond enthalpy is 10 and it is 10. So 10 plus 10, it is 20, total 20 kilojoules per mole. Here intermolecular interaction is less, so less than 10. Suppose if it is considered 5, so 5 into 2, 10. So it is 20, it is 10. 20 minus 10, 10. It is greater than 0. Is it clear? Intermolecular interactions between the pure components and solution, if it is considered, so here intermolecular interaction is less, When intermolecular interaction is less, the energy required to break the bond is also less. So therefore, enthalpy of mixing will be greater than 0. Whereas in this case, volume mixing, how it is greater than 0? See, when intermolecular interactions in pure components, suppose 10 ml of A plus 10 ml of B is mixed, the resulting solutions will be greater than 20 ml. Suppose 10 ml of A plus 10 ml of B, then it gives 20 point something ml, 20 point something. So it is great. How it is possible? So when 10 plus 10 is equal to 20 only, but here we are getting 20, more than 20. That is called positive deviation. Positive deviation. Why? Because intermolecular interactions are there. So if it is same, intermolecular interactions are same, then the volume will be same. When intermolecular interaction in the solutions are less, so when it is less, the volume undergoing expansion. Intermolecular interactions are very less, it cannot hold tightly, so therefore little volume is expands in solution case. So solutions minus pure components will be positive in this case. So therefore in positive deviation, intermolecular interactions are less and the remaining total vapor pressure will be greater, enthalpy of mixing will be positive, and this is also positive, mixing is also positive. In case of negative deviation, it is opposite, less than 0, less than 0, less than calculated. Calculated and total vapor pressure. Total vapor pressure will be less than PA plus PB. This is about ideal non-ideal solution and non-ideal solution showing positive and negative deviations. Let us explain one more by taking an example. This positive and negative deviation. That means examples of this. So, in case of positive deviation, the intermolecular interactions will be lesser. Suppose I am considering mixture of ethyl alcohol plus acetone or benzene or cyclohexane, whatever you can have. In ethyl alcohol, how it is the structure? Alcohol, no? ROH, ethyl alcohol, C2H5OH, ethanol, C2H5OH, ethyl alcohol. Ethanol molecules are there. So in ethanol molecules, some hydrogen bonding will be present already. So hydrogen bonding present in the ethanol molecule. When acetone is added, these acetone molecules which enter into the ethanol, so some of the hydrogen bonding will be broken. So when the hydrogen bonding breaks, so automatically these molecules now will having high tendency to escape. Therefore, the vapor pressure will be more. It is called positive deviations. So this type of solutions shows the positive deviation. So negative deviation means how? So negative deviations, let us take one example of negative deviation. So chloroform, CHCl3, chloroform plus acetone, CH3CH3Cu. In pure components, the intermolecular interactions is some values. Intermolecular interactions is different. When it is mixed with each other, a new hydrogen bonding are formed in the solution. So due to the formation of some new bonds, hydrogen bonds are formed. So intermolecular interactions will be more. It is increased in solution. So in solution, the intermolecular interactions will be greater. So these molecules do not have a tendency to escape the liquid surface. And so as a result, the vapors produced are less, hence vapor pressure will be less. It is said to be negative deviation. So after mixing the two components, if intermolecular interaction begins, that means vapor pressure will be less. So when the two components are mixed, so in that case, if the intermolecular interactions are weakened, then which becomes more tendency to escape the liquid surface, hence vapor pressure will be more. So these are the chloroform and acetone are the examples of a negative deviation. So this is the example of negative deviation. So positive deviation, negative deviation. Ideal solution means similar. Benzene plus toluene. C6H6 benzene plus C6H5CH3 benzene and toluene, chlorobenzene, chlorobenzene plus bromobenzene, etc. So some of the examples. So 5 to 6 are some number of examples you can note down in this case. Ideal solution and non-ideal solution. Difference. Non-ideal solution showing positive deviation and negative deviation. The difference between these 2 points. And the last one is azeotropic mixture. Definitions with example. Non-azeotropic mixture. Next one is simple definitions with examples. Azeotropic mixtures. Azeotropic mixtures. What is meant by azeotropes? Azeotropic mixture means so here very simple definition of this azeotropic mixture means the solutions are the liquid mixtures which boils at constant temperature without distill the compositions, without change in its compositions are said to be azeotropic mixture. That means, so whatever the compositions are present in the solution, in the liquid mixture, if it having same composition in vapor phase, that is called azeotropic mixtures. Suppose if you have taken some alcohols and water mixtures, mixture of water and alcohol, and it is heated, what happens? Alcohol and water, when it is heated, what happens? First the alcohol vaporizes, right? Now initially the vapor phase containing only the vapors of alcohol, not the water. So initially the composition is only alcohol, whereas water composition is 0. The mole fraction of water is 0 initially. As the time increases, when the concentration of alcohol in the solution decreases, so here, okay, in a closed vessel, I have taken a mixture of water and alcohol. Mixture of alcohol and water, A and P, 2 components I have taken. So one is alcohol, and this is, let's assume that it is water. When it is heated, first the A molecules vaporizes. Initially, vapors of A are produced. So when alcohol undergoing evaporations, its composition, its concentration in the solution decreases. When its concentration decreases, gradually, when temperature is increases, some of the water vapors also undergoing evaporations. So the composition contains initially whatever the composition of A and B in the solutions, let's say 95% of alcohol. 95% alcohol if it is taken, 95% of ethanol, ETOH, C2H5OH. 95% of ethanol when it is distilled, when it is heated. So here the vapor phase also containing the same composition, that is 95% of alcohol. The liquid mixtures, the mixture of liquids are the solutions which boils at constant temperature without changing its compositions are said to be azeotropic mixtures. Is it clear? Yes. Now, this is the definition. Azeotropic mixture means the mixtures, liquid mixtures are azeotropic solutions. The solutions which boils at constant composition. The solutions which boils at constant temperature without changing in its composition, is said to be azeotropic mixture. The solutions which boils at constant temperature, that is first part, constant temperature and without changing in its composition, the composition in vapor phase as well as in solution phase must be same. So that is called azeotropic solution, and it is of two types. It is of two types. One is maximum boiling azeotrope, maximum boiling azeotropes, and minimum boiling azeotrope, minimum boiling azeotropes. So what is meant by maximum boiling and minimum boiling azeotropes? So first of all, what is meant by the boiling point? Boiling point is nothing but it is the temperature at which the vapor pressure becomes equal to atmospheric pressure. Let us consider a curve, vapor pressure versus temperature, and assume that this is the atmospheric pressure and these are the two different liquids, liquid A and liquid B. The liquid A, one represent this is the positive deviation, the solution which showing positive deviation and solution showing the negative deviation. As you know that solution showing positive deviation means intermolecular interactions will be less, so its vapor pressure will be more. That's why, so I am consider this is a higher vapor pressure. A is at higher vapor pressure and B is at lower vapor pressure. Now when temperature increases, it gradually increases and reaches a particular point, particular temperature at which the vapor pressure will be equal to atmospheric point. So this is called boiling temperature. So boiling temperature for positive deviations is less, whereas the boiling temperature of negative deviations will be more. So therefore we can say that the solution which showing negative deviations, the solution showing negative deviations are called maximum boiling azeotrope, maximum boiling azeotrope, whereas the solution which showing positive deviations is called as minimum boiling azeotropes, and these are the examples: 20.2% HCl, 95% of ethanol. Okay, is it clear? Yes. In this concept, the first point is definition: azeotropic mixture, the mixture which boils at constant composition without changing the composition. The simple, the liquid mixture which boils at constant composition, that means constant temperature without changing its composition. It's of two types: maximum boiling, minimum boiling. Maximum boiling means the solution which showing the negative deviations are called as maximum boiling, and the solution which showing positive deviations are called as minimum boiling azeotropes, and these are the example. So this completes the part 1 of the solution chapter. In the next class we will start the part 2, that is colligative properties. Okay, in the next class we will start the colligative properties.